an extension of section 7.1 from the textbook. It's not actually in the textbook, but I think it is important to discuss the difference between distance traveled and displacement. So distance is a scalar quantity that refers to how much ground an object has covered during its motion, whereas displacement is actually a vector quantity that refers to how far out of place an object is, and it's the object's overall change in position. So like, let's say that I'm sitting in my living room and I'm sitting on my couch. This is my couch, and sitting there, and I get up and I walk the 20 feet to the kitchen. Okay, so that's 20 feet to the refrigerator. Okay. And then I go back and I sit back down. Now I walked 20 feet to the refrigerator and 20 feet back. So my distance traveled would be 20 feet plus 20 feet would be 40 feet. However, my displacement would actually be 0 because I ended up in the same place that I started. Another example could be, let's say you're in a car. And you drive 15 miles east, okay? So you drive 15 miles east. And then you drive 10 miles, so you drive 15 miles east, and then you drive 10 miles west. Okay, so just in the opposite direction. Your total distance traveled would be the 15 miles plus the 10 miles, so 25 miles total would be your distance traveled. However, for displacement, it would actually be just from where you started to where you ended. So you would actually be only 5 miles in the east direction would be your displacement. So let's look at some of these examples where we're going to look at what the distance traveled is versus what the displacement is. So if Ms. Dorset walks 4 meters east, why don't we draw this in a picture? So how about like in the XY plane? I'm going to label this north, south, west, east. Okay, so Ms. Dorset walks 4 meters east. Okay, 2 meters south. Four meters west. And 2 meters north. So we can see when we map that out, I basically end up walking in a circle or a square. And my total distance traveled would be adding up each of those distances. So each of the magnitudes of those vectors, right? Because we're given a distance as well as a direction. So when I walk 4 meters east, so 4 meters plus 2 meters plus 4 meters plus 2 meters, I would actually end up walking, what is that, 12? 4 plus 4 is 8. Yeah, so 12 meters would actually be the total distance that I've walked. But we can see from drawing this picture in the XY plane that my total displacement would actually be 0 meters. Okay, let's look at the next example. So if Ms. Dorset walks 3 meters east and 8 meters north. Let's draw the picture. Okay, so I'm going to use different colors for the different vectors. So 3 meters east and 8 meters north. So what is the total distance that she's walked? Well, total distance would be that 3 meters plus the 8 meters, so 11 meters. However, the total displacement would actually be this distance right here, which, well, that would be the magnitude of the displacement. So the displacement would actually be that vector right there, which this should look like tail to tip method of adding vectors. So we want to, when we find the displacement, we want to find what the magnitude is of that vector as well as the direction. To find what that displacement vector is so that we can find the magnitude and the direction of that vector, I suggest drawing another picture which would then allow us to add the vectors using parallelogram method. Remember, we can think about moving vectors around the xy plane, meaning we can think about redrawing the vector or moving the vector so that it's in any vector so that it's in standard position, meaning that its initial point is at the origin. So we already have that first vector that has a magnitude of 3 meters and is pointing in the east direction. We already have that in standard position, right? So this first vector in component form would be 3, 0. And then the vector that represents walking 8 meters in the north direction, we could move that to be in standard position. And in component form, that would be 0, 8. So then to calculate the displacement vector, we could easily see that that displacement vector would have a horizontal component of 3 and a vertical component of 8. Well, let's go ahead and find the magnitude of that displacement vector. So to find the magnitude, I'm going to do the square root of 3 squared plus 8 squared would be approximately 8.544 meters. And then let's also get the direction. So the direction would be inverse tan. I'm in quadrant 1, so I'm just going to have the inverse tan of 8/3. Which is approximately 69.444 degrees. And since we're using direction like north, south, east, west, okay, this angle right here would be theta, so we could say 69.444 degrees north of east. Okay, so displacement, the magnitude of the displacement would be approximately 8.544 meters, and the direction to describe the displacement would be approximately 69.444 degrees north of east. Okay, so let's map this out in our picture. Okay, so Ms. Dorset walks 5 meters west. Six meters north. Four meters east. And 2 meters south. Okay. So distance traveled, we could just add up each of those distances. So 5 plus 6 plus 4 plus 2 gives me 17 meters. Okay, so 17 meters would be the total distance traveled. However, displacement would be, and I believe I'll be in quadrant 2, but I'm not totally sure. This is just a sketch, but would be that vector right there. That would be my displacement vector. So we want to find the magnitude as well as the direction of our displacement vector. So to do that, I'm going to redraw the picture so that each of the vectors that represents my movements are in standard position. So then I can have the vectors in component form and then just think about adding those vectors together to find my displacement vector in component form, and then from there find the magnitude and the direction. So the first vector, 5 meters west, was already in standard position. It would be -5, 0 in component form. And then the 6 meters north would be 0, 6 in component form. 4 meters east would be 4, 0 in component form, and then the 2 meters south would be 0, -2 in component form. So then to find the resultant vector, that would be adding up all the horizontal components, so -5 plus 0 plus 4 plus 0, and then adding up all the vertical components, so 0 plus 6 plus 0 plus -2. So we get -1, 4. Okay, so that makes sense then for our resultant vector, our displacement vector, terminating in quadrant 2. Okay, so this point right here where that vector terminates would be the point -1, 4. We want the magnitude. So the magnitude would be -1, square root of -1 squared plus 4 squared, which would be the square root of 17, or approximately 4.123 meters. And then I'm going to use, so I want to find this angle. Okay, so theta star, if I take the inverse tan of 4 over -1, right, that's going to give me this negative angle here in quadrant 4. So if I were to add 180 degrees, that would give me, I'll call that the angle theta, although I think I'm going to want to use a different angle to describe the direction. So if I add 180 degrees to inverse tan of -4, that gives me the angle 104.036 degrees. Why don't we subtract 90 degrees from that angle? So really, I would be adding 90 degrees to inverse tan of -4. And then that would give me this angle right here, which is approximately 14.036 degrees. And then I can say 14.036 degrees west of north. You could also find this angle instead, so that you could say whatever that measurement is, north of west. So there are different angles that you could find in order to describe the direction. I'm going to use, for describing the displacement, as being 4.123 meters, 14.036 degrees west of north. Okay, so I hope that helps with showing you the difference